Hey everyone, welcome to Akaiki's webinar series. In the last session, we explored what AI agents are and how they're transforming enterprise workflows. In today's session, we'll explore something just as exciting and fundamental, which is the field of computer vision, or commonly known as CV. We'll dive into what CV is, how these systems work, how it can be developed, some of the challenges or fundamental tasks they try to solve, and where to finally apply them. I'm Bhumika. I work as a data scientist here at Akaiki.
Myself, Vishnu. I work as a senior data scientist. I have experience in building computer vision applications.
Alright, let's start with the basics. What exactly is computer vision and how would you explain to someone with no technical background?
So CV is, or computer vision is a subset of AI which uses perception to process and make an understanding of the world around us. So we generally use images or videos and then we make some understanding around it. But these systems are specifically designed to do specific set of things. For example, identifying a cat or a dog, or basically differentiating between a cat and a dog, which is a very simple example.
Yeah, wait. Continuing with the example of cats and dogs, right? I think it's something that's very simple and almost instinctive to humans, but maybe a difficult task to mimic. So, how do these systems go about mimicking the way we see and interpret visual information?
So CV systems and humans are very similar when you look from a bird's eye perspective. So human see, understands, and learns from past experiences, right? So computer vision does it in a very similar way. CV system uses cameras while humans uses eyes to see. We use brains to process what we see. CV uses computers with algorithms built into it to process what we see. And then CV systems uses data to learn, or past data or historical data to learn from the data, while humans use past experiences to learn from the data. A few examples that you can see in your real life is your unlock system in your phone, where you look at your face and then it unlocks, and self-driving cars, or attendance systems in your office, AI cameras, all that stuff.
Okay, taking the example of self-driving cars, right? It's pretty clear that they deal with visual information, either in the form of streaming images or video frames. So that kind of gives us a clue on the type of input that these CV systems expect. But what's really happening behind the scenes? How do they take this image data, process it, and make some sense out of it?
So CV systems are basically complex software systems. Like any software system, it's just a piece of code, right? So things are a little different here because you have some math involved. So at the start, it's always the input. So we take the input from an image. It could be an image, it could be a video, it could be a series of images, or it could be X-rays, CT scans, MRIs, all that stuff. Once we have the input, we process the input. We do some adjustments like color, brightness, contrast, etc. And then we give it to an ML model, which is optional. Some CV systems do not use machine learning models, but some systems do. The ones they do, they make some decisions around it. We usually use machine learning to make decisions when we have an ML model. It used to be classical models, but recently they've changed into deep learning.
I think deep learning models have been playing a pretty major role in the computer vision field, right? So why is this the case, and how do they really improve the system's accuracy compared to the traditional ML models?
Now, DLs and ML, the big difference, there's a huge difference. Traditional models, which we use humans, and they do some feature engineering. You have to extract features manually from it, and then you feed it into an ML model. That's how classical ML works. But in case of deep learning, that's not the case, because you feed the data and you let the model itself learn data from it, or itself learn the features or patterns from it. And then you have a final layer of making decisions also. So in a nutshell, it's very versatile.
Okay, that is pretty impressive how they are able to mimic the way humans interpret and process, right? But can you explain a few foundational tasks that these CV systems are built to solve?
Now, I can think of 4 foundational tasks. One is detection, segmentation, post-estimation, and classification. Now, detection, coming into these topics, right? So detection is basically you're trying to find an object in space. You're trying to, let's say you have an image and you want to find a person who's inside, who's in the image. So that's how a detection works. So usually get bounding boxes, or basically you draw bounding boxes around it. You get coordinates of the boxes. Second one, segmentation. Segmentation is very similar to object detection, but instead you get an RY, get a region of interest. It could be an arbitrary shape. Very similar, but not the exact. The concept, the underlying concept is a little different. Classification is where you try to differentiate between the objects in an image. Let's say you want to differentiate between cats and dogs. That's one problem. Hot dog and not hot dog. That's another problem. And finally, pose estimation. Pose estimation is finding the pose of an object in the space. Let's say you have a person or a person dancing, and then you want to find how the person moves. So what you do is you put key points around the joints, and then you process that image. So you get key points on each frame of the person in each frame.
Got it. So it's clear that all of them have their own roles to play. But can they be used in combinations, and how do they come together to build a complete system?
They can be used in combination. In some cases, they are used individually as well. If you take cases of individual use cases, it's easy, very easy to think of. In a closed space, how do you find number of people inside that? That's a very independent use case. Not exactly independent, but it's a very crude example. When it comes to bringing these things together, another example I can think of is license plate detection in a traffic stop. So what you do is you need to find license plate numbers. In order to do that, you need to break down the problem into multiple parts. One is detection, and one is reading the license plate itself. So detection is it's finding the license plate within the image or the video, and you are trying to get the characters in the license plate, which is OCR, optical character recognition. So that's another problem which can be drilled down further, can be separated out as detection and recognition. But yeah, this is how multiple things come together and be a whole system together.
Got it. So can we speak a little on the development process? So let's say we have a problem to solve and we have divided it into subtasks like detection and OCR that we spoke about. So how do we go about building a complete system around this, and what's the end-to-end pipeline like?
So as in any software development process, the first thing to do is define the problem. So once you have a solid definition of what the problem is, then it becomes easier to solve. You can break it down into multiple parts and solve them separately and put it together. Now, next step, more like 1.5, if there is a need of an ML model, what people generally do now is get something that is open source, which is already pre-built and ready to use for the use case that you have in hand. Because it takes a lot of overhead development of your head. You don't have to reinvent the wheel. In some cases you might have to, but most of the cases open source models works as out of the box or with some error rate. Third thing is to get and clean the data. So acquisition and data cleaning is one of the most important jobs when it comes to building any ML system, or any AI system. So the better the data is, the better the output. Garbage in, garbage out, right? These are usually done by data team. There will be separate data management team with a few data scientists. Fourth one is building and evaluating the model and the system. So if you take it as an entire system, you have to build the entire software. And the model as well, a bunch of data scientists will be working on the model, testing it, building, testing, evaluating, all that stuff. The next step is deployment. Straightforward, you deploy it in cloud. Depending on the use case, you deploy it on the cloud or the edge or on-premise. And then finally, you need to monitor the system, because not every ML model or every system is perfect. So you need to have some continuous level of monitoring as well.
Makes sense. Can we speak a little more on what the data collection process looks like, and is it hard to get the right kind of data?
It depends on what kind of data you are trying to collect. Right kind of data is usually hard to get because you have a lot of data on the internet, on your enterprise servers, or other sources, open source sources as well. Internet data is usually subject to copyright, so you can't really use that. And then enterprise, it is available, but you will have to clean it up. There will be a lot of cleaning involved. And some cases, for example, X-ray, CT scans, data like that, which are not available to the public, but they are usually available to specific set of people, like hospitals or clinics or something like that. So yeah, it depends, and it depends. That's the just it depends.
At the same time, it's also important to account into variations, right? Like making sure the different lightings are taken care of, angles, perspectives are taken care of. So, okay, let's assume we have the right kind of data. So, how do you go about training the model, and is transfer learning something that's always a go-to?
Right. So for training the model, important thing is data cleaning. So once data cleaning and annotation and all the stuff is out of the way, you can proceed for building a new model. But most of the cases, retraining works because you don't have to reinvent the wheel. Most use cases are already built. But certain use cases you might not get good models, or there might not be models even exist. They might not even exist. So in those cases, you'll have to retrain it from scratch.
Got it. So, assuming you were able to train a good model that with very good accuracy, but before pushing it into production, right? What sort of benchmarking would you do? And are only technical metrics involved, or any business level metrics involved as well?
Yeah, two sets of metrics, technical metrics are there, which usually data scientists folks mess with, which are usually precision recall, accuracy, etc. All those stuff directly depends on the problem. Classification uses precision recall, accuracy. Detection uses MAP. Segmentation uses IOU and other metrics. All that stuff. And then second, business KPIs, which is more of a business perspective. So A/B testing, where you roll out two features, one with the change and one without the change, and then you compare the groups. You compare the business KPIs within the groups. Compare A between B, and then you find if it has improved or not. So that is one way of testing it as well.
Got it. So I think naturally the next question is where and how to deploy these models, right? What are some of the key factors that decide whether it should be a cloud deployment, an on-prem deployment, or in some cases even on an edge device?
Three cases that I would look is latency, cost, and data privacy. Privacy is where you don't want to share the data with anyone. You don't want the data to go out of your hands, as in you don't want it to be with a third party person. Could be PII data, or could be X-rays or data related to that. In that cases, I would do it in on-prem, where you have a server system located inside the building itself, maybe, and then you have it there. When it comes to latency and you want the results quick, you want to put that model inside a device, probably a sensor. Edge is the obvious solution.
Okay.
And then all these video processing systems as well, usually people go with Edge because cloud-based solutions can get very expensive. And then cloud, I would go with one-time processing or API calls when the cost is not a big problem. And then if that is the case, then it's cloud deployment.
Okay. So let's say now the model is live and it has been deployed and it's doing pretty good on the real-time data, but is this really the finish line? And what sort of monitoring would be needed, right? Like model monitoring or data monitoring?
Post deployment, it's not a full stop yet, so it's like a comma, and then you continue. Monitoring, you will have to do monitoring on the system, the entire system itself and the model itself. The entire system, it's a software problem. On the model itself, none of the models are good, as in the data will change with time. So you will have to retrain it again and again. You have to keep a tab on the model until it's mature to do most of the things. Not all models are the greatest things. Not all the models are best in the market. So you'll have to keep retraining. You'll have to keep monitoring it basically.
So scalability is a common issue with all sort of deployments and software development, right? Can you give a few real-world examples where CV is making an impact in today's world?
Yeah, a few examples I can think of is manufacturing is a great example, medical care, then retail, three examples probably. And then when you drill it down from manufacturing, you have the use cases within manufacturing are also a lot. For example, defect detection, where you want to find a defect in a production line. Let's say you are creating cars and then you want to find dents in the car created or paint defects or something like that, or PCB soldering defects, or if you are misplacing components within PCB, that's another example that you can do. Healthcare, two subdivisions that I can think of is medical imaging and then administrative applications. Applications which help in administration. Medical imaging, automating radiologist's job, as in helping out radiologists to find, to process X-rays, MRI, CT scans, all that stuff. Then when it comes to administrative applications, insurance, processing insurance documents, medical records, etc., all that stuff, all the things. So when it comes to retail, what I can think of is you can do customer behavior analysis, where you track people in a closed showroom where they are walking around, and then to see where they are lingering or what path they take, just to do some layout optimization where the customer is looking at, or what product the customer is looking most at, or a bunch of customers are looking at. So you can do those in retail as well.
Got it. I think that's a great mix of use cases and sectors that CV can solve, right? The information that you gave about how these models work behind the scenes, how to deploy them, and real world use cases were really informative and interesting. So thank you for that, Vishnu. We hope this session helps you as an enterprise understand where you can start adopting or applying computer vision to solve some challenges and just improve your overall efficiency. We look forward to seeing you in our next session. Thank you.